In this video, we are going to discuss about the positional encoding in transformers. Before getting started, let us understand the significance of transformers. Consider the sentence, he loves to travel and explore new countries. Here, you can clearly observe travel has a specific meaning. Okay, consider this sentence. The wheels of the car need an alignment after hitting a rough pothole during travel. So the travel word has different meanings in different sentences. So the word context changes based on the surrounding words and the meaning of the surrounding words. So the embeddings of travel must be different here as well as here. So whenever we are trying to convert into other language, the translations of travel must be different. So is that really the same case when we try to convert into French? Let us observe. Okay, let us observe the translation of he loves to travel and explore new countries into French. So it has given some word which I can't spell. Okay, now we have the other translation. The wheels of the car need an alignment after hitting a rough pothole during travel. You can clearly observe that if you have basic knowledge of French, you can understand that travel is related to voyager. Okay, you can also try it in Google Translate. See, now if you are considering travel here, you cannot see voyager word because the meaning of travel is different in this word and in this sentence. Here, travel give me trajet. So based on the context, we need to have different meanings for the word. And the other thing, if you're considering an RNN structure, see whenever we are trying to have English to French or English to any other language translation, you can clearly observe that the length of input and the length of output is different. So there is always difference in length. It's not that we always have the fixed length or the same length as input. So it may be different. So if you are considering RNN structure, it fails. This is the disadvantage of RNN, and the other disadvantages as I already told in the previous video, which is vanishing gradients and bottleneck problem. Okay, this is stuff about RNN and a little bit about transformer network. So we are using transformers. Let me show you the architecture of transformers in order to avoid all this stuff. So we use transformers. Okay, this is the basic model architecture for transformers. So here you have inputs and we have input embeddings. This is the encoder block. This is the decoder block. This is transformer. That's it. So you have an encoder, you have a decoder, and you have input embeddings, and you'll be having positional encodings, and you have output embeddings and positional encodings. Okay, let us divide all these parts. So in this video, we are just going to discuss about this part, which is giving input, taking input embeddings, and producing positional encodings and giving it to encoders. So our part is just this box which are circled. Okay, so before going let us understand how we give input to an RNN or any other architecture. Okay, suppose how he is a student. Basically, we understand strings, but computer just understands series of numbers. And especially when you are dealing with machine learning applications, we represent everything in the form of numbers or arrays. So he will be having some positional numbers. Like let us consider the embedding size to be 4. So it may have 2.0, 3.8, 4.2, and 1.2. And each will be having some other positional embedding. A will be having and student will be having different positional embeddings. Okay, as I already told you, transformer is a parallel way of processing. So transformer architecture is designed in such a way that all these words are given at parallel. So you'll be giving he is a student. Unlike RNN structure, we'll be giving sequentially, like we give he initially, then we give his, then we give student. Sorry, next we give a and then student. In transformer architecture, we give all those words at the same time. Okay, So it will give us time efficiency. Okay. So, but what is the disadvantage of this method? See, suppose I consider he is a student and I read the sentence in reverse order. Student A is he. As we are giving in parallel, the system does not understand the order of words. Unlike in sequential data, we use he. So the system understands that he is the first word. And then we give is, then we give A, then we give student. But in parallel way of processing, we are not giving anything. So we need to have the order of sentence, okay? And the second thing is positional encoding. What is positional encoding? Suppose I give a very big sentence and I write he is something. So he should refer to student because we are talking about student, right? So he must like if I write Ram is a good student and I write some so and so text, he goes to school daily. So he must refer Ram here. Okay. So in order to understand that, our model needs to have knowledge of previous words or the words which are after it. In one way, we avoided it in RNN by using bidirectional RNN. But here we are not discussing about RNN, LSTM, or any other thing. Here it's completely parallel. So we introduce what is called positional encodings. Suppose have an embedding layer, like if I'm representing he in the form of embedding like 4.3, 3.6, 2.1, and 3.20 something. So we are adding an extra vector of the same size representing the positions. Like if I add 1.0, 0.8, 2 point, sorry, 1, 0.6 and 0.12. So these represent position. These are not exactly, we'll be having a formula which I'll be discussing later. So these are positional embeddings. So we add this to our encoding. We'll be adding it to input embedding and we'll be getting some output. So that will be our positional encodings. Let me show you the animation of that. See, initially we have I'm a student. So our embedding vectors were 1, 2.2 and so on. Okay. We are adding some positional embeddings. So one, I'll be discussing later how we got this positional vector, but initially understand this. So we are adding positional encodings to our embeddings. We'll be getting new output which is embeddings with encodings. Okay. So we are adding these two in order to get this. So we need to take care that positional encodings should not affect our embeddings. Like if I add some 1000, so this will definitely affect my training because it will completely change the context. So the researchers have used a formula which is uh, position by 10,000 power 2 I by d. Okay, just understand what is it. So, like sine of this and cos of this. So what exactly is this? Leave out the formula. Just understand what is it. Like simply you know that cos and sine will produce the numbers from -1 to 1. Okay, and our embeddings may have different values. So whenever we are adding positional encodings to our embeddings, since our values are just from -1 to 1, it does not affect the context a lot. Okay, this is the advantage of positional encodings. And why we need positional encodings? Let me go to the previous slide. So why we need positional encodings is, see, he is a student. So if we are using the formula, this is our positional encoding, right? This is the same size of our vector, embedding vector. So here what we do is, we'll be having this size to be embedding dimensions, okay? We alternately apply sine and cos. Like if this is first word, this is sine of this value. This is cos of this value. This is sine. This is cos. This is sine. This is cos. This is sine. This is cos, and so on. So what we are doing, we are applying sine of position by 10,000 power 2I by d. What is this formula? Researchers have tried with different formulas and they got finally into this formula which worked well for our transformer architecture. So if you are considering the position, position is the word. Like suppose we are representing, this is a student. He is a student, right? Suppose these values are 256, 128, 23 and 0. So position is this word. This is position. Okay, and I is the ith dimension. Like, see, this is position, right? This is 256 and 10,000 power. See, our embedding size is, suppose it is of size d. Okay, so I will be like, if you are taking the first word, I will be 0, right? So it will be 2 times 0 by d. Okay, okay, this is d square size. Okay, so it will be 256 by 10,000 power 0 by d, which is 0. So you'll be getting some other value. So I is the position in the embedding, and POS is a position of the encoding. Like simply suppose you have numbers 256, 128, 23 and 0. See, position represents these values and I is the dimension. Like suppose we are having 10th value in the encoding. So I is 10. This is about I and position. And what is D? D is square root of embedding size. What is embedding size? Suppose we are having 300 dimensional embedding. So D will be root of 300. So researchers have gone through many researches and they found that using D as the root of embedding size worked very well. So you can also use d square, d cube or any other thing. But out of all this, root of embedding size has worked. They have made research on different values. They tried d square, they tried only d, they tried d power 1 by 3 and all, and they finally came to conclusion that root of d worked very well. This is about positional encoding in transformers. So let me show you the animation once again. Let me clear all the content in this slide. So let me take the laser pointer. Okay, so you have 1 2.2, these are the embeddings. In reality we'll be having 256 or 300 dimension. We'll be having positional encodings and you observe that all these positional encodings are less than or equals to 1 and greater than or equals to -1 because we are using a sine and cosine function. See, if we are going to that formula, we'll be applying sine here. See, it will be sine of so and so by 10,000 power 2I by d. Okay, this will be sine of 2 sorry position by 10,000 power 2I by d. So this will be cos of that value. This will be sine of that value. This will be cos of that value. Okay, this is about positional encodings. So what happens is, see, as we are using position value, suppose we are having I am a student 256, 128, 26 and 30. So by using this formula and adding all these vectors, we'll be getting a new embedding with encoding value. So this is able to represent the positional value of numbers. Like it can understand the positions, like student is here. Understanding in the sense, it will be representing in different numbers. Like initially our numbers were 1, 2.2, 4.6 and 8.3. Here we got updated values. And after training that, we found that this positional encodings helps in training, like helps the model to understand where the words are. This is about positional encodings in transformers. In the next video, we'll be discussing about encoder and decoder layer, and finally how transformers are used to calculate the output, and how transformers is used in ChatGPT. Not exactly ChatGPT, uh, in the GPT model, and how they have used generative AI and all the stuff. Thank you.